We're going to tackle the mathematical idea of relations, and especially equivalence relations. So first off, let's talk about what relations might be. So if we have two real numbers, we can say that, say, x is related to y in lots of different ways. X might be less than y might be one more than the square of x. We might say x and y are equal. We have symbols for all of this. If we have two integers, a and b, we can say a divides b. That's a relationship between the two. A and b are of opposite parity. Again, that's a relationship. Or a is congruent to b mod 3. That's also a relation. We could go into geometry and we can have a line in 3 space, and it can be related to a plane in 3 space if the line lies on the plane, if it's parallel to the plane, or if the line intersects the plane in exactly one point. We could take two triangles and say that they're related if they're congruent to one another, if they're similar, or if they have the same area. So in all of these examples, the common thread is we have two sets, A and B might be the same set, like we might just have triangles as our set, or we might have lines in 3 space and planes in 3 space, two separate sets. But we've got two sets, and we're taking an element of one of the sets, and we're saying that it's related to another element in the other set in some kind of manner, right? So it turns out that these come up a lot in math, way more examples than what I have here. So it would be a good idea for us to define them. So a relation R from a set A to a set B is the subset of the Cartesian products A cross B of A and B. So that's the ordered pairs where we're taking an element from A as the first entry and an element B from B as the second entry, right? So it's this set of ordered pairs, and we say A is related to B. So any ordered pair that's in this relation, A is related to B. And we write it A with an R and then a B, right? So we use this capital R for relation. If you're still using just a capital R without using that second line on it for the real numbers, great time to start using that second line so that you don't get the relation R and the real number R confused. So similarly, we can say A and B are not related if they're not in this subset of Cartesian of ordered pairs from our Cartesian product. So we write that with A and then R with our handy not slash through it, B. So let's take an example of A being the set XYZ and B being the set 1, 2. So a possible relation would be the subset of ordered pairs from the Cartesian product of A and B that consists of x2, y1, and y2. Now, this is a relation from A to B, and in this case, x is related to 2 because x2 is a part of my relation. However, x is not related to 1 because x1 is not an ordered pair in my relation. So for any two sets, A and B, the empty set and the entirety of A cross B are always subsets of A cross B. So the empty set and A cross B are relations from A to B, always. So when we talk about relations, it's really handy for us to talk about the idea of the domain of the relation and the range of the relation. So when we talk about the domain of the relation, we write it with the DOM of R. Now, what this is it's the subset of the elements in A that show up in the relation. So it's the set of all of the elements of A such that the ordered pair AB is a part of the relation for some B in that set B. And the range is the same thing, except for we're looking at the subset of B such that AB is in the relation for some A and A. So this is all of the elements in B that show up somewhere in the relation as well. All right, let's take an example of this. So we have the relation x2, y1, y2. To find the domain, what we're doing is we're looking for all of the first elements that show up that are distinct. So I have an x and I have a y, and that's it. So the domain of R is the set xy. Similarly, for the range, I'm looking at all the second elements and looking at what shows up unique and new. So I see a 2 and I see a 1. So I have the set 1, 2, and that is the entirety of the range. Now, Z was a part of our set A, but it doesn't show up in this relation. So Z is not a part of the domain of R. Now, in math, we always want to be able to undo the things that we do. So it's important for us to talk about the idea of an inverse relation. So we have a relation from the set A to the set B. The inverse relation of that relation R, we write it with that superscript of -1, the same way we do for a function. And the inverse relation is going to go in the reverse order of the original relation. So since R, our original relation, went from A to B, the inverse relation will go from B to A. So the way we define it is the inverse relation, R inverse, is going to be the set of ordered pairs BA such that the ordered pair AB is in the original relation R. So really all we're doing is changing the order of the ordered pairs in our relation, and we have our inverse relation. So our relation R that we've been working with, x2, y1, y2, the inverse relation on that, we just flip the order of things showing up. So we see that we have 1y instead of y1, we have 2x instead of x2, and 2y instead of y2. Now, sometimes we talk about a relation on a single set. So way back in the beginning, we were talking about the relation on the set of triangles. Now, say we have a relation on just a single set. So I'm going to have a relation on the set A. Then what we mean by that is the relation goes from that set to that set. So we have a relation from A to A. So what that means is the elements in the ordered pairs that make up the relation are going to have the first and the second coordinates coming from the set A. So if I had the set 1, 2, 3, 4 as my set A, then a relation on A might be the set containing the ordered pair 1, 2, the ordered pair 1, 3, the ordered pair 2, 2, and the ordered pair 2, 3. So let's take a set A that has the elements 1 and 2 in it. Now if I look at the Cartesian product of A with itself, then that's the set that contains the ordered pairs 1, 1, 1, 2, 2, 1, and 2, 2. It has 4 elements in it. So we can count the number of subsets of the Cartesian product of A with itself and see that there are in fact 16 possible subsets, ranging anywhere from the empty set up to the entire set of A cross A with all 4 elements involved. So of those 16 possibilities, we've got some of them listed here. It's really any subset of those 4 elements, from none of them to up to all 4 of them. And all of those possibilities are all relations. So there are 16 possible relations on A. So when we have relations, it's a great thing to be able to say something about them. So we want to be able to say if a relation is reflexive. So what we mean by that is a relation R, we say it's reflexive if x is related to x for every x in A. Notice we're defining the relation on a single set A here. So x has to be related to itself for every x in A. And if that's the case, then we say the relation is reflexive. We also can take a relation on that single set A, and we can say it's symmetric. And we say that if X is related to Y, then Y is related to X for every X and Y in A. In other words, if XY is an ordered pair, that's a part of my relation, then YX must also be an ordered pair, that's a part of my relation. We also sometimes want to say that the relation is not symmetric, and we can easily see that if we have an ordered pair, say WZ, that is a part of the relation, but the ordered pair ZW, the reverse of it, is not a part of the relation. Another thing that we like to be able to talk about with relations is the idea that they're transitive. So sometimes they are, sometimes they aren't. So to determine if a relation is transitive, we need to determine if we have two ordered pairs, XY and YZ, that is, X is related to Y and Y is related to Z as a part of our relation, then X is related to Z. So we're taking the first element from one of the pairs and the second element from the other pair, and the second and first elements agree. So this is basically the same type of idea of the equal sign being transitive, where if you have X equals Y and Y equals Z, then X must equal Z. Same deal here, except we're going to be writing them in ordered pairs to show the relationship rather than putting an equal sign between them. Or we'll be putting an R between them instead of an equal sign between them. So X, Y, and Z, one really important thing, they don't have to be distinct. So if I have 1 is related to 2 and 2 is related to 1, then 1 must be related to 1 in order for my relation to be transitive. So let's take a look at an example. So I have a relation, R1 here, that has the ordered pairs AB, BA, and CA in it. And it's a relation on the set S that has elements A, B, and C. I also have a relation R2 on that set that has ordered pairs AB, BB, BC, CB, and CC. Similarly, R3 relation on that same set has elements AA, AC, BB, CA, and CC. And relation 4 on that same set has elements AA, AB, BB, BC, and AC. Now, to determine if any of these relations are reflexive, remember reflexive means that A needs to be related to A, B needs to be related to B, and C needs to be related to C. So that means ordered pairs AA, BB, and CC need to appear in the relation. And the only one that satisfies having all three of those ordered pairs present is relation 3. So relation 3 is reflexive. Relations 1, 2, and 4 are not. Now, reflexive is the easiest thing to check of these three. Checking to see that a relation is symmetric takes a little bit more work. What you need to do to find out if it's symmetric is you need to look at an element in the relation. So in relation 1, the first element is AB. Now I know if it's going to be symmetric, that means that BA must also be an element in that set. And it is, it's the second element. And then both of those elements, they're satisfied for the symmetric relationship. However, there's another element there. So I need to check for CA. If CA is present, then AC must be present, and AC is not. So it's not symmetric. And you basically do that until you've accounted for all of the elements in the relation to check and see if their symmetric partner is there. So in relation 2, I have AB, so that means BA must be present, and it is not, so relation 2 is not symmetric. Relation 3, AA is its own symmetric pair, so it's good. AC means that CA needs to be present, and it is. BB is its own symmetric pair, and CC is its own symmetric pair. So relation 3 is also symmetric. Relation 4, AA is its own symmetric pair. AB is present, so BA must be present, and it's not. So relationship 4 is not symmetric. Now, for transitive, this might be the hardest one to check. So what you're looking for are two-ordered pairs where the second element in one of them is equal to the first element in the second one. So I'm looking at relation 1. The first element is AB. The second one is BA. The B's match up. So that means that I have AB and BA both present. So that means that AA must be present, and it's not. So relation 1 is not transitive. Similarly, I'm looking at AB and BB in relation 2. So that means the B's match up in the middle and AB must be present. So it is. Then I can look and I can see AB and BC are present. So AC must be present, and it is not. So relation 2 is not transitive. As soon as you have one example of a way that it's not, then you move on, all right? You've said it's not, you're good, you have your proof, you have your counterexample for it being. Then relation 3, I have AA and AC. The A's match up in the middle, and I have AC. AC is present. Then I have AC and CA. The C's match up in the middle, and AA must be present, and it is. And I have CA and AC, and the A's match up in the middle, so CC must be present, and it is. And there's nothing with B's in it other than BB. And so relation 3 is in fact transitive. Relation 4, AA and AB, A's match up in the middle, AB must be there, it is. I have AB and BB, so AB must be there, and that works out. I have AB and AC, the B's match up in the middle, AC must be there, and it is. I have AA and AC, the A's match up in the middle, AC must be there, and it is. I have BB and BC, the B's match up in the middle, and BC must be there, and it is. So relation 4 is also transitive. Now, here's some more examples. I'm going to leave these for you to explore and decide about them being reflexive, transitive, and symmetric. The answers are there for you to check your answers along the way. So let's talk about this idea of distance. So if I have two real numbers, A and B, when I take the absolute value of A minus B, what I'm really doing is finding the difference, or the distance, sorry, between A and B. So the distance between 2 and 4.5 is the absolute value of 2 minus 4.5, or the absolute value of negative 2.5, which is 2.5. So 2 and 4.5 are 2.5 units apart from one another. So we can have two real numbers plotted on a number line, and we can be looking at the length of the segment between them. That's really what we're talking about when we talk about the distance. So the distance between negative 2 and 3, we can find the absolute value of negative 2 minus 3 and find that it's 5, which is the length of that segment between negative 2 and 3. So we might be defining a relation where we're looking for real numbers, A and B, and we're saying that they're related if the absolute value of A minus B is less than or equal to 1. What that's really saying is that A is related to B if the distance between A and B is at most 1. So let's think about this in terms of reflexive, symmetric, transitive. So we can take a look at this, and A is going to be related to A. Well, what that means is the absolute value of A minus A, that's what we're looking at. We need that to be less than or equal to 1. A minus A is 0. The absolute value of that is 0. 0 is less than or equal to 1. So A is in fact related to A, and that's true for any real number. So I have that my relation is reflexive when I define it as the distance between A and B being at most 1. Now, for symmetric, let's take a look at that. So I'm going to say A is related to B. Like, what does this mean? It means A minus B is less than or equal to 1, the absolute value of that. Well, with absolute value, b minus a and a minus b, they're equal to one another. So if a minus b is less than or equal to 1, so is b minus a. So a is related to b. If a is related to b, then b is related to a. So the relation here is also symmetric. Now, the transitive property. Now, if you think about two real numbers that are less than 1 apart, and then another number that's less than 1 apart further than away on the other side, it's pretty easy to convince yourself that this isn't actually a transitive property. So A is related to B, B is related to C, but A is not related to C. So to show that it's not transitive, all we need is one example. We need a counterexample. So let's say I have the real numbers 3 and 2. 3 is related to 2 because the distance between them is 1, which is at most 1. 2 is related to 1 because the distance between them is less than or equal to 1, at most 1. So that means that 3 would have to be related to 1 in order for this property to be transitive. But the distance between 3 and 1 is actually 2, and 2 is not less than or equal to 1. So 3 is not related to 1, and the relation that we have here is not transitive. Now, why we care about all three of these things. So there's a special type of relation that is incredibly useful in math called an equivalence relation. A relation that we have is called an equivalence relation if it's reflexive, symmetric, and transitive. So the most basic example of this you've been using for a long time now is the equals relationship. So if A is related to B, what we're saying is A equals B. That's an equivalence relation. And you actually learned the idea of reflexive, symmetric, and transitive in regards to this equals equivalence relation. So what we're doing now when we talk about equivalence relations is we're really generalizing this idea from this most basic equivalence relation that you learned earlier in life. So let's take a look at the set A that has the numbers 1 through 6, the integers 1 through 6 in it. And we're going to have a relation that has these ordered pairs below in it. Now, we can go through and we can check this and we can see that it is reflexive. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6 are all present. All right. It is symmetric. You can go through and check that. It is transitive. You can also go through and check that. And consequently, this relation is an equivalence relation. So sometimes we want to talk about like things to do with an equivalence relation. So say we have an equivalence relation and we have some element in our set A that the equivalence relation is defined on. Then we put square brackets around A and we're calling this the equivalence class of A. All right. So what this is doing is it's telling us all the elements in A that are related to this element A. So the equivalence class of A, little a, element in AA, is equal to the set of all X elements in A such that X is related to A. So let's take a look at this example that we had before with the relations. So if I want to know what's related to 1, what I'm doing is I'm looking for when is 1 the second element in the ordered pairs in the relation. So it happens 3 times. It happens when the first element is 1, when the first element is 6, and when the first element is 3. So when I talk about the equivalence class of 1, it is the elements 1, 3, and 6, because those are the elements that came first when 1 came second. And if I go through and I do that for all of the elements, so let's take a look at 2 really quick. So when 2 is the second element, the first element is 2, and then it happens again when the first element is 4. So 2 and 4 are the equivalence class for 2. So you can go through and you can do that for all of the numbers, and if you do, you'll end up with these equivalence classes. Now hopefully you fairly quickly go, but the equivalence class for 1 and for 3 and for 6, they're all the same. And so that means that there's really only one equivalence class there, so we only need to talk about the equivalence class of 1, and in doing so, we're also talking about the equivalence classes of 3 and 6. And then 2 and 4, you notice that those are also identical, so we only have to talk about one of them. And then the equivalence class for 5 is unique from all the rest. So there are 3 distinct equivalence classes, and those are the equivalence class that has 1 in it, the equivalence class that has 2 in it, and the equivalence class that has 5 in it. This is not a All right, let's take a look at an example. So we have a relation R. It's defined on the integers by x is related to y if x plus 3y is even is an equivalence relation. So let's take a look at this. All right. So we want to know if it's reflexive. Is R reflexive? So we're going to take a look at some A in the integers, and we want to know if A is related to A. That's how we check for reflexive. Well, A is related to A if A plus 3A is even. Well, A plus 3A equals 4A, which equals 2 times 2A. And since 2A is an integer by the definition of even, then A or 4A is even. And so we have A is related to A and R is reflexive. Now to check symmetric, we need to assume that A is related to B. That means that A plus 3B is even. So we have A plus 3B equals 2K for some integer K. And we can solve that for A and find that A equals 2K minus 3B. Now remember what we're trying to show is that B is related to A. So really that B plus 3 times A is even as well. So we've solved for A. And when we take a look at B plus 3A, well, substituting in 2K minus 3B for A, we have B plus 3 times the quantity 2K minus 3B. We can distribute out the 3, we can condense like terms, combine like terms, and we can factor out a 2 and see that B plus 3A is in fact even, since 3K minus 4B is an integer. So we have B is related to A. So we assumed that A was related to B, and we showed that B is also related to A. That means that our relation is in fact symmetric. Finally, to show that our relation is transitive, we are going to assume that A is related to B and B is related to C. So in this example, what that gives us is A plus 3B and B plus 3C are both even. So A plus 3B equals 2K, B plus 3C equals 2L for some integers K and L. And then we're going to add them together to find that we have A plus 4B plus 3C equals 2K plus 2L. Now, notice that we're trying to show that A is related to C, and so what we really want is A plus 3C. Well, the A and the plus 3C are in here, so all I do is subtract 4B across, and I have A plus 3C equals 2K plus 2L minus 4B. Factoring out a 2, I have 2 times the quantity K plus L minus 2B. Since K plus L minus 2B is an integer, then A plus 3C is even, and consequently, A is related to C. So our relation is transitive. Since we've shown that our relation is reflexive, symmetric, and transitive, we've shown that our relation is an equivalence relation. Now let's take a look at the equivalence classes for this equivalence relation. So if we take a look, choose an integer. So let's start with 0. 0 is the favorite integer, right? So we throw in 0. Well, x is related to 0 what that means, that's what we mean when we're looking for an equivalence class. We're looking for all the x's that are related to 0. What that means in these terms is that x plus 3 times 0 is even. Well, 3 times 0 is 0, so what we're really looking for is x is even. And we know what the even integers look like. They look like the set containing 0, plus or minus 2, plus or minus 4, and so on. So say I have an integer a that's an even integer of some sort, and I'm looking for its equivalence class. So I'm looking for all the integers that x is related to a. Well, in this case, that means that x plus 3a is even. But a equaled 2k, so I can substitute that in. So what I'm really looking for is x plus 3 times 2k is even, or x plus 6k is even. Well, it's pretty clear that 6k is doing its part to be even, and so what I'm really looking for is when x is even. So again, I have an equivalence class that is all the even integers. So 0, the even integers, all the even integers have the same equivalence class. So let's look at an odd integer and see what happens. So let's look at 1, our favorite odd integer. So I want to look at the set of elements that are related to 1. So what I'm really looking for is x plus 3 times 1 is even. Now x plus 3 is even is what I'm really looking for. 3 is odd, and I know that if I want to get an even and I'm adding something to an odd, it needs to be an odd. So I need to have odd plus odd. So that means that x must be odd integers. And I know those plus or minus 1, plus or minus 3, plus or minus 5, so on. In fact, I can do that for a generic odd integer too. So say a is 2l plus 1. Now, substituting in 2l plus 1 for a, I can see that the 6l part is going to be even. And so I have something plus an even plus an odd. So something plus an odd, it needs to be odd. So really, whenever a was even, my equivalence class was the even integers. And whenever my a was odd, then the equivalence class was the odd integers. So there are in fact 2 distinct equivalence classes, and I can just sum them up as being the equivalence class of 0 and the equivalence class of 1, or the equivalence class of choose your favorite even integer and choose your favorite odd integer. So here's another example. I'm not going to talk through it. I'm going to let you guys take a look at it, and we will talk about it all you want in the future.